Hello, welcome to Unit 7, Lesson 5, Ready, Set, Go, maintaining your identity. So, the first thing we see on this page is a diagram, and it has a few things shown on here for us, right? It talks about point B, which we see right here. So let me point out that point B. So it gives us x and y, and it shows where x and y is on the triangle, right? That we have the opposite side of theta and the adjacent side of theta. And then it shows s as the arc length created by angle. And then, of course, we have our radius here as well, the hypotenuse of the triangle. So question 1 says, find that radius. Well, since this is, and it gives us that the x value is 512. So if we know it's 5, remember that's the adjacent side of this angle is 5, because that's where x is, and the opposite side is 12. So the easiest way to find r, I think, is just do Pythagorean theorem, right? Our two side lengths squared will give us our radius squared. So 5 squared is 25, and 12 squared is 144. So we get 169 equals r squared. Now, this is a Pythagorean triple, so if you recognized it off the top of your head, that's great. But the radius then, the radius is 13. That is the square root of 169. Okay. Find theta to the nearest thousandths of a radian, right? That's 3 decimal places. Well, if we know all 3 sides of the triangle, we can use any of the sides to find theta. I'm going to use 5 and 12 because we already have them, but we could use that 13 if we wanted. So I'm going to say tan of theta is our opposite 12 over adjacent 5, or y over x, right? Tan of theta is y over x. Tan of theta is y over x. So, and it says to the nearest radian, so make sure your mode on your calculator is in radians. So, my next step to get theta by itself is take the inverse tan. I'll put theta on my left side, I guess. Inverse tan of 12 over 5. Now, we do have to be really careful when we do inverse on our calculator using sine, cosine, or tangent. Any of them could give us sort of false answers depending on which quadrant we're talking about. However, since we're dealing in quadrant 1, right here we're quad 1, everything is positive, we can trust the answer that our calculator gives us. So when we do tan inverse of 5/12, we get, it says 3 decimal places, so we get theta equals about 1.176, and I don't round that up because it's followed by 0.005. So that is theta. Okay, find the arc length, right? S, using the formula r times theta. So remember, arc length, just to sort of backtrack where that formula is coming from. Arc length is sort of the measure of our angle out of a whole circle times circumference. Well, when we're in radians, it's the measure of our angle over 2 pi. That's how many radians are in a full circle, times 2 pi times the radius. So those 2 pi's end up reducing away. That's why it's just our angle times the radius. So since our radius was 13, we do 13 times 1.1176. I'm going to use parentheses. 1.176. So S equals approximately. Now, I haven't cleared my calculator from when I did inverse tangent, so I'm just going to keep that exact number and multiply it by 13 to get as exact a decimal as possible. And I got 15.28. I'll go to 3 decimal places because that's what we did for the angle. So 15.288. Okay. Now it doesn't tell us any units, so I'll just keep it at that. Describe point P using our radius as our first component. Well, our radius is 13. And our angle as our second component. So 1.176. Okay, now we want to use point B as the radius again. So 13, but this time using the arc length as our second component. So 15.288. Okay, question 2. So once again, we have similar numbers. It's really important to distinguish our quadrant first, or not necessarily first, but certainly before we find our angle. So 5, positive 5, right, x, y. So positive 5, but negative 12. We're going to be down in quadrant 4. So positive 5, negative 12. We're down in quadrant 4. So let's find r first. Well, we're going to get 5 squared plus negative 12 squared equals r squared. So our radius comes out the same because we still get 25 plus 144, which is 169. So our radius, and radius is a distance, so radius is always positive. So our radius is 13, once again. But this time our angle is going to be different. So I'll use tangent again. Tan of negative 12 over 5. See, here's the problem. Oops, what am I doing here? Tan of theta equals negative 12 over 5. So there's one problem with this. Our calculator doesn't know the difference between negative 12 over 5 and 12 over negative 5. So sometimes what it's going to accidentally give us is this angle right here. It's going to accidentally give us negative 5, 12. So it's going to accidentally give us that angle sometimes. So let's see what happens here. Now, not all the time. Sometimes it gives us the correct angle, and this one will be fine. But we have to use sort of logic to decide which. I'm going to do this in purple because it is going to give us the correct angle. But we do have to be really careful. So theta equals tan inverse of negative 12 over 5. So let's go to our calculators and see what tan inverse of negative 12 over 5 is. So inverse tangent of negative 12 divided by 5 gives us a theta of roughly negative 1.176. And that answer's okay. If we want it to be a positive answer, we can do with that. But this did give us that angle right there. Theta equals negative 1.176. So notice it's the same angle we got as above, because it's just saying the direction is going downward instead of upward, right? So this one that we're going up, we're going counterclockwise. And here it's saying we're going down, we're going clockwise. So it makes sense that that's that same angle. If we want a positive angle, so this is fine. If we want a positive angle, we want to add a full circle, add 2 pi. So I'm going to add 2 pi to my answer so that we have a positive angle, which gives us 5.1071. So I'm going to keep it at 5.107. 3 decimal places. So if I add 2 pi, I get that positive angle. It doesn't say that theta has to be positive, so it's okay to use the negative version. Okay, so now find the arc length. So this is where I'm going to use the positive angle, and I'm going to do 13 times my 5.107. S is, because we're going to assume that this is going, well, actually, I guess we don't need to assume it's going either direction, but if I use this, I get 66.393. So essentially, what I just found here, let me draw it off to the side. For question C, we have, let's draw a little circle. All right, not my best circle, that's okay. So what we just found is this length here. We found this as S. If we had used the negative 1 point, if we use 13 times negative 1.176, that's the arc length we find. But we would want to use positive. Always positive. So if we did sort of use that other number, it's giving us that smaller length. Okay. So describe point B using our theta. Again, we actually could have two answers. I'm going to use our positive theta, so 13 for R, 5.107 for theta. But you could use 13 and then negative 1.176. That's okay as well. Describe point B using the radius and arc length. So 13, and I'm going to use 66.393. Again, if we're traveling clockwise, clockwise, then we would use 13, and then we would actually get that 13 times 1.176, we're going to use a positive, we're going to get 15.288 again, the same number as before. So this is misleading. So misleading. Since this leads to quadrant 1. Right, so I'll kind of sort of put that as, so do not use. Do not use. There we go. And that's what we get from that 13 times 1.176, right? So don't use that because that looks like it's quadrant 1 when we are in quadrant 4. That's not a problem with answer D because we have the negative sign on the angle. But when we're talking about arc length, we're using a positive distance. And so we need to go counterclockwise so that we know how far we're going. Okay, question 3, find R. So here we have another Pythagorean triple. But if you don't recognize it, you can do negative 6 squared plus negative 8 squared, which gives us 36 plus 64. And 36 plus 64 is 100. So the radius is 10. All right, the radius is 10. Find theta to the nearest thousandths in a radian. Again, let's make sure we know which quadrant this is. So negative 6, negative 8, we're double negatives. That's going to be quadrant 3. So this one we're actually going to get an incorrect answer for, right? And I'll explain why. It's not incorrect. We just have to, we can't just trust our calculator to give us the correct answer right away. This is saying our x value is negative 6 and our y value is negative 8. And this is the theta that it's going to give us. It's going to give us just the triangle theta. So let's say tan of theta equals, and I could use the radius instead actually, but I'm going to keep with tangent. So equals negative 8 over negative 6. Well, that's the same thing as tan inverse of 8 over 6. Those negative signs reduce out. They're not needed, and even if you leave them in when you calculate, your calculator is still going to read it as positive 8 over 6. So when we do inverse tangent of 8 divided by 6 or negative 8 divided by negative 6, we get 0.927 but that is quadrant 1. So really we need to think, okay, how far are we really? Well, this is pi. So to get this angle right here, we have to do pi plus that angle we just got plus point. What did we get? We got, let me just look at my calculator. We got 0.927. So I want to add pi to that. So our angle is roughly, so plus pi, roughly 4.06, and it goes 88, so I'm going to round it up to 9. Good. And remember, a whole circle is 2 pi, or about 6.28, so it makes sense that we get something a little around 4. Since halfway is 3.14, we can see we're past the halfway point. So there's our angle. So now find our arc length here. So we're going to take our radius, which we said was 10, and we're going to multiply it by our angle, 4.069. Or if you want to use I'm going to use the 88 here, or 89, because when I multiply this by 10, if I want it to still be 3 decimal places, it's nice to have that extra one. So I have 40, let me write that a little neater, 40.689. We round up because it's 6888, so I round up. Okay, describe point B using the radius. So our radius is 10, and our angle, so 4.069. Describe point B using the radius, 10, and our arc length, 40.689. All right, question 4. We have another Pythagorean triple. Here we're in quadrant 1 because everything's positive. So quad 1. Which makes us smile because we don't have to really think about, do we add 2 pi, do we add pi, do we subtract anything? We can just go ahead and do our inverse trig. So 9 squared plus 40 squared. Well, 9 squared is 81. 4 times 4 is 16. So 40 times 40 is 1,600. So we get 1,681, which is a perfect square. This is another Pythagorean triple. The radius is 41. Okay. So find theta to the nearest thousandths of a radian. Well, tan of theta equals y, 40 over x, 9. So theta equals tan inverse of 40 over 9. Remember, my calculator is still in radian mode because it wants us in radian. So inverse tan of 40 divided by 9 should give us about 1.34. Now it goes 9,4, so I'm going to keep it at 9. Find S using the formula, or find our arc length. So we're going to take our radius, 41, and we're multiplying it by 1.349. So again, I'm not even going to clear my calculator. I'm just going to hit times 41. So I get an arc length of about 55.329. 329. And it really goes 3287. So I'm rounding that 8 up to a 9. Okay, find the point B using our radius. Well, we said our radius is 41. And our angle, 1.349. Find point B using the radius, so 41 again. And our arc length, so 55.329. Okay, and there's the end of question 4. So now we're on to the step problems, and it says the cofunction identity states that sine of theta equals cosine of pi over 2 minus theta, and cosine of theta equals sine of pi over 2 minus theta. So let's keep those in mind as we do it. I'll even take a little screenshot of them so we can rewrite this on the next page as we scroll down. There we go. We just keep that in mind. So it wants us to complete the statements using this cofunction identity. Oops, sorry. So this is almost more of a practice of adding and subtracting fractions, right? I have 3 over 10. So if I want to do pi over 2 minus 3 over 10, 3 pi over 10, I need to make sure I have a common denominator. So I'm going to multiply this by 5 over 5, so that my fraction becomes 5 pi over 10 minus 3 pi over 10, which becomes 2 pi over 10. I'm going to go ahead and reduce that to pi over 5. But if you wanted to leave it as 2 pi over 10, it really shows the similarities there. So pi over 5. Okay, good. So this next one, we have pi over 2 minus pi over 3. So again, we multiply. We need these to be common denominators. So this one, I actually have to change both of my fractions. So let's make this one. The least common denominator here is 6. So if I want this to be a 6, I need to multiply by 3 over 3. And I need to multiply this by 2 over 2. So that gives me 3 pi over 6, right? That's still a half, minus 2 pi over 6, which goes to pi over 6. So my final answer there is cosine of pi over 6. Okay, so now 2 pi over 9. Oops, sorry. Let me write pi over 2 first. Pi over 2 minus 2 pi over 9. Again, I need to find a least common denominator. Let's use 18. So I'm going to multiply by 9 over 9 and 2 over 2. So that gets me 9 pi over 18 minus 4 pi over 18, which is 5 pi over 18. So let's fill that in. Sine of 5 pi over 18. Notice that it changed from giving me sines to cosine, but I still am subtracting our angle from pi over 2. So that did not change. Okay. So pi over 4. So pi over 2 minus pi over 4. So I only have to change this one because my least common denominator here is pi over 4. So I get 2 pi over 4 minus pi over 4, which gives me pi over 4 again. In this one, we probably actually could have done logically without thinking, without having to do the addition or subtraction, because remember, that's the 45, 45, 90 angle, like the special right triangle, where the sine and the cosine values are the same. So sine of pi over 4 is always going to equal cosine of pi over 4. Now, it's not true if I have negatives involved, because then the signs are off, but where it's positive, those ones are the same. Okay, pi over 2 minus pi over 12. So let's change this 2 by multiplying by 6 over 6. So we get 6 pi over 12 minus pi over 12, which gives us 5 pi over 12. Okay, now we have decimals. We're still going to keep this the same way. We're going to do pi over 2 minus 0.715. Now, pi over 2, we can put that in decimal form as well, I suppose. So we're going to use this for basically all of these. So pi divided by 2 is roughly 1.57, let's go to one decimal place, so one more decimal place, so 1.571. But I'm not going to use that number. I'm going to keep it as pi over 2 in my calculator and just subtract 0.715 so that I get the most exact answer possible. Since it gives me 3 decimal places, I'll continue to use. So I'll use 8, 5, and then it's 5, 7, so I'm going to round that up to 8.6. Sorry, I think I said 8. So it was 0.856. Okay. So our next one, pi divided by 2 minus 0.393. So pi divided by 2 gives us about 1.7. So then minus 0.393 gives us roughly 1.178. I rounded that last digit up. Okay, question 12. Pi over 2 minus 1.423. So pi divided by 2. So 1.571 minus 1.423 gives us about 0.1477. So 148. I'm going to round up. Here, pi over 2 minus 0.57. Now notice it's 0.57, and so is this. So this one's going to work out really nice. I'm going to just make this 1. 1 point, I'll even show 0, 0, 0. Technically, it rounds up to 1, I suppose. So I'll put the 1.00. Okay. Now 14 starts some new questions. Let's go. Oh, sorry, not scrolling. There we go. So I messed up my page here. Okay, 14 says, use Pythagorean theorem identity. So sine squared theta plus cosine squared theta equals 1 to find the value of cosine, given that pi over 2, that theta is in between pi over 2 and pi, and it can include both of those values. Okay, so this tells us we have sine of 3/4, with sine of theta equals 3/4, which could be quadrant 1 or 2, but here we want to be in quad 2. That's telling us that cosine is in quad 2, which means cosine should be negative. So quadrant 2, we're someplace right here, right? Now I could do this. It says use Pythagorean theorem identity, so we're going to do that. But remember, I could do this by thinking, okay, my radius is 4, and my y value is 3, and I need to find my x value, and I could use Pythagorean theorem, right? I could do 4 squared equals 3 squared plus x squared, and I'll show that just, right? So we get 16 minus 9 equals x squared. So we end up with 7 equals x squared, which means x is square root of 7, only because we know x is negative, right? We're going to do negative square root of 7, which then we could do negative 7/4. So that's going to be our answer, but let's show how we do this using Pythagorean theorem. So we know sine of theta is 3/4. So sine squared of theta is going to be 3/4 squared plus cosine squared theta equals 1. So let me zoom up. So 3/4 squared, that's 9/16 plus cosine squared theta equals 1. So now let's move this 9/16 to the other side to get cosine by itself. So cosine squared theta equals 1 minus 9/16. Well, I'm going to change that 1 to a 16/16 so I can subtract my two fractions. So cosine squared theta equals 7/16. So now I want to take the square root of both sides, right? So when I take the square root of both sides, I end up with cosine of theta equals, well, the square root of 7 doesn't simplify, so I'm going to leave that as 7 over, the square root of 16 is 4, but quad 2, use negative cosine. So I'm going to say that cosine of theta is, so our final answer is cosine of theta is negative square root 7 over 4. There we go. Okay. Now it says use the quotient identity. Part B says use a quotient identity, which is tan of theta equals sine of theta over cosine of theta, the given information in your answer in part A to calculate the value of tan of theta. So tan of theta equals sine of theta divided by cosine of theta. Another way to think that is sine of theta over 1 times 1 over cosine of theta. And I'm only doing that because sine of theta over 1 is just 3/4. But 1 over, right, 1 over cosine of theta is the same thing as negative 4 over square root 7. Right? So times negative 4 over square root of 7. So our 4's reduce out. That works out really nicely. And we're left with negative 3. Actually, I'll put that negative just in the front, kind of. Negative 3 over root 7. And then we always rationalize. So this answer becomes negative 3 root 7 over 7. And I'll write that over here. Negative 3 root 7 over 7. Okay, question 15. So it says we're given this interval. So in between 3 root 2 and 2 pi, that is quadrant 4. So in quadrant 4. Okay, so now we know it's in quadrant 4. It does that. Let cosine of beta equal 12 over 13. Find sine of beta given that it's in quadrant 4. Okay, it doesn't tell us which way we want to do this. So we could use the Pythagorean theorem identity again, right? We could say that sine squared of theta equals plus 12 over 13 squared equals 1. So that would give us sine squared theta equals, 12, I'll do it in 2 steps, plus 144 over 169. I'm going to write my 1 as 169 over 169. Okay, so sine squared theta equals 169 minus 144 over 169. I'm subtracting those tops. Sine squared theta equals, well, that gives us 25 over 69. So sine of theta, the square root of 25 is 5. And the square root of 169 is 13. So let's think, is sine positive or negative in quadrant 4, right? So we're down here where cosine is positive, right? 12 over 13, but sine is negative. So sine is negative. So we're going to have negative 5 over 13. Okay, and then part B, where's my part B? All the way down here. It says find tan of B. Well, we'll use the tangent identity there. Again, this sine of theta over cosine of theta. And this time I won't do the reciprocals. I'll just put them right in as they want. So we just found out that this is negative 5 over 13. And we know that cosine is 12 over 13. So I have a fraction divided by fraction. I'm going to multiply that by the reciprocal. 13 over 12. Okay, so those 13s reduce. We're left with negative 5 over 12. So tan negative 5 over 12 tan is negative in quadrant 4, so that checks out. Okay. Question 3 wants us to do cosine of pi over 2 minus our angle. So in order to find sine of beta. So we should get the same answer. We already know beta. We already know sine of beta is negative 5 over 13. Okay, so the fastest way to get this, we want to think this is essentially going to shift it up a quadrant, right? So if I'm looking right here, we're going to shift up a quadrant, which will give us a positive value instead of a negative value for sine. So sine of beta would be 5 over 13 instead of negative 5 over 13. Okay. Question 16, it says, write tan of theta in a different form to see if the given identity is true. So we want to test to see if tan of theta times cosine of theta does in fact equal sine of theta, and it wants us to change tangent. So let's change tangent to sine of theta over cosine of theta, and we'll keep everything else the same. So times cosine of theta equals sine of theta. So is this actually true? Well, here we see that cosine in the numerator and cosine in the denominator will reduce out. So we're left with just a sine of theta on this left side and a sine of theta on this right side. So this is true. So we have it true. Okay. Perform the indicated multiplication to see if you can get the Pythagorean identity for question 17. So let's multiply. So 1 times 1 is 1. 1 times negative cosine. Beta is negative cosine of beta. And here we get positive cosine of beta. Right, we have a difference of squares here. Negative times positive, we're going to get negative cosine squared beta. And does this equal sine squared of beta? So our difference of squares causes these two terms to add to 0. So we're left with 1 minus cosine squared beta equals sine squared beta. So we want to move that cosine over to the other side. So we get 1 equals sine squared beta plus cosine squared beta. So yes, we get the Pythagorean identity. Awesome. Question 18. Use your work in problem 7 to prove 1 plus, sine of alpha times 1 minus sine of alpha equals cosine squared of alpha. So it says use your work, so we're going to multiply again. That's what we did in problem 17. So 1 minus sine of alpha. Now we have plus sine of alpha, and then minus sine squared alpha. Is that equal to cosine squared alpha? So this is extremely similar, but this time our minus sign and our plus sign, those ones add to 0, and we're left with 1 minus sine squared of alpha equals cosine squared alpha. And again, we're going to move that negative sine squared over to the other side. So we get 1 equals, and it doesn't matter if I put it first or second, cosine squared alpha. So yeah, we once again proved that this is true. We get the Pythagorean identity again. Pythagorean identity. Okay. Okay. 19. Rearrange the terms in the equation until you get the Pythagorean identity. So it gives us sine squared of w minus cosine squared of w equals 2 sine squared w minus 1. So here we have some like terms. It doesn't matter if we bring things to the left or right. I'm going to subtract. Let's subtract sine squared w from both sides. So I get negative cosine squared w equals, well, 2 minus 1 gives us 1 sine squared w minus 1. So now I'm going to add the 1 to both sides, plus 1 to both sides, right? And I'll do this in a couple steps, actually. So I get 1 minus cosine squared w equals sine squared w. And now I can add that cosine to both sides. Right, so I'm going to move that over by adding it to both sides. So I get 1 equals sine squared w plus cosine squared w, and there's our Pythagorean identity. Okay, question 20. Our directions say find the two solutions in degrees and the two solutions in radians for each of the equations. And it wants, when it says 2, right, we're going to use positive values. So we're using theta between 0 and 360, including 0 and 360, and 0 and 2 pi, including those. And it does not want us to use a calculator. So let's start with sine of 1/2. Sine of theta equals 1/2. So let's plot where these could be. So we're positive sine, which means, so y is positive. So here y is positive, right? And here y is positive. So it's saying that if our hypotenuse is 2, actually let's make our hypotenuse 1, and our side length's 1/2. Our y value is 1/2. So we're not using our calculator, so this must be a special right triangle if we can do it without it, right? So which special right triangle has a side length of 1/2 in it? Well, that's the 30, 60, 90. So if we want, we could even say, hey, this is negative square root 3 over 2, and this one is positive square root 3 over 2. So this is quadrant 1 and quadrant 2. So what angle is across from that 1/2? Well, it's the 30-degree angle. So in degrees, it's 30 degrees. Now if I know this is 180, and that in their angle is 30, that means we have to subtract. So and 150 now in radians, which is down on this next page, 30 is equivalent to pi over 6, and 5 pi over 6 is equivalent to 150. Okay, question 21. So again, we're dealing with sine, but this time we have negative 1/2. So now we're looking in quadrants 3, right? Quadrant 3 and quadrant 4. Now we could actually use our answers. We already know that when we have this value of negative 1/2, that we're creating a 30-degree angle right here. So 30 degrees, negative 1/2. So we figured that out in the last one. So if this is 360, well, we're 30 less. Remember, this is 180, we're past it, so we're 30 more. So 180 plus 30. So 180 plus 30 is going to give us our angle in quadrant 3, which is 210 degrees. And here we can do 360 minus 30, because remember our answers need to be, we can't use negative 30 because our answers need to be in between 0 and 360. So, and 330 degrees. So that's our degree answer. Our radians, well, the equivalent to 30, remember that's a pi over 6. Pi is equivalent to 6 pi over 6, so we're pi over 6 more than that, which means we're 7 pi over 6. And, I wrote pi instead of 6, there we go. And 11 pi over 6. Remember, a full circle would be 12 pi over 6, so we're 1 below that, 1 pi over 6 below that. Okay, let's do, so here we have a new special right triangle. So we have cosine of positive square root 2 over 2. So cosine is positive in quadrant 1 and quadrant 4. So cosine of square root 2 over 2, that means the x value is square root 2 divided by 2. So this is going to give us a 45-degree angle because it's a 45, 45, 90 special right triangle. So in quadrant 1, we just use the exact 45. Here, remember this is 360 total, so we get 360 minus 45 for quadrant 2, which is 315. 315 degrees. Good. So equivalent to 45, that's pi over 4 in radians. And remember, a whole circle is 8 pi over 4. And we're pi over 4 less than that, so, and 7 pi over 4. Okay, question 23. So here we have sine of theta equals negative. So we're negative sine. So we're going to be in quadrants 3 and 4. Quadrant 3, quadrant 4, negative square root 3 over 2. So that's our y value. Negative square root 3 over 2, negative square root 3 over 2. Well, the angle that creates that opposite side is a 60-degree angle. So here we have 180 plus 60, which gives us 240 for quadrant 3. And here we're going to use 360 minus 60 to get 300. So, and 300. So equivalent to pi to 60 degrees is pi over 3. So if we think of 3 pi over 3 plus 1 pi over 3, we get 4 pi over 3. And 6 pi over 3 minus pi over 3 is 5 pi over 3. Okay, question 24. So this one wants tangent, and tangent is equal to negative 1. So let's think where tan comes out negative. That's when x and y are opposite signs. So it's in quadrant 2 and quadrant 4. Here we have positive over positive, which gives us a positive. And here we have negative divided by negative, which gives us a positive. So quadrant 3 and quadrant 4, quadrant 2 and quadrant 4 are where tan is negative. So x over y, so it must be negative x over positive y, or negative y, negative y over positive x, or positive y over negative x. But the absolute value of x must equal the absolute value of y. That's how we get that 1. So for this to be true, this must be a 45, 45, 90 triangle, since our two side lengths are equivalent in that 45, 45, 90. So here we have positive square root 2 over 2 and negative square root 2 over 2. And that would be a 45-degree angle. And here we have positive square root 2 over 2 as the x and negative square root 2 over 2 as the y. And we create that 45 angle there. So let's think, if this is 180, that means we're 180 minus 45 because we're not quite there, which would give us, I need to create a little more room here, 180 minus 45 is 135 degrees. And here, remember, we're 360. So 360 minus 45 gives us 315. So pi over 4 is equivalent to that 45 degrees. So here we're going to get 3 pi over 4 because we're above that pi marker, and 7 pi over 4. Okay, that's 24, so let's move on to 25. So this time, tan of theta equals square root 3. So we have positive. So let's think where tan is positive. We're in quadrants 1, where tan is positive, and quadrants 3. Quadrant 1 and quadrant 3. So now let's think, how did we get, so tan, remember that's y over x. So how do we get this square root 3 over 1? Well, that's coming from the 30, 60, 90 triangle. So 30, 60, 90, let me sketch just the basic 30, 60, 90 down here. Not quite to scale, but that's okay. So let's say that my hypotenuse is 2 for this triangle. Let's say this is 60. This would make this square root 3, and this would make this 1. Now the other option, so that's right here. That's actually what we're seeing. Square root 3. Well, let's actually we want the y value to be square root 3. So I probably should have oriented this a little differently. Let's redraw it. Because we want the y value to be square root 3. So I want my 60 down here. 1 and, sorry, I decided to use 2 here, which makes this 1. So if I have a y value, y over x of square root 3, that means I have to have an x value of 1, which makes this a 60-degree angle with a hypotenuse of 2. Now I could have used square root 3 over 2 and 1/2. Those two would end up reducing. So that gives me a 60-degree angle, which means this also must be a 60-degree angle. Remember, we have 180 here, so we get 180 plus 60, which gives us 240. So in radians, that's pi over 3 and 4 pi over 3. And that is question 25. Hopefully you found this video helpful. Thank you for watching.